see that. And what I want to show you now is some examples of these sorts of deposits. So these represent a greenstone belt. And when we started off, we went out and had a look at the deposits and how brittle the deformation was, what the wall rock alteration was, and so on. We did what Lindgren would do in the old days. We used our common sense and we said, oh look, we think this is forming maybe at 5 kilometres depth or something like that. It might be 250 degrees or 200 degrees, something like that. Then we look at another one, we think, oh, that might form. This one here's got weird minerals in it, might form down there. And then we go to another greenstone belt and we find more and more and more. This is our way, so we might have 3 greenstone belts. And then what we did, we had a lot of PhD students, a lot of people wanted to come. We had a big centre at University of Western Australia, so we had a big centre. So every year we had an average of 40 PhD students in our group every single year, just doing economic geology. So we took about 30 or 40 of these. So we put a PhD student looking on this one, this one, this one, this one, with a view that we'd try to put this all together. We had the biggest PhD group in economic geology in the world, I think, and we had up to 17 different nationalities in the group at any one time. So we had a whole lot of people studying, so we had a fantastic chance to look at all these different deposits at different depths. And we know that these could be vertically extensive systems because if we look at some of the big deposits, so Homestake, the deepest part of the mine was about 1.5 kilometres. It's just been cut off a little bit on the edge. So Morro Velho in Brazil here was 2 kilometres, and Colar went down for 2.5 kilometres. And the important thing was Homestake bottom because it was in a fold, so it was an abandoned iron formation, so the folds didn't go down any deeper. Morro Velho is in a sort of a faulted, it's in a alteration zone related to a big structure, and it could have been mined, if they'd have drilled this out in a modern thing today and knew it went down 3 kilometres, they could have put a shaft over here and worked it, or they could have declined on it and it would have been worked. So it was still economic at those grades if they had put the shaft, but what they did of course put the shaft here, then they had to put an underground shaft and then another one down through here, and so eventually this becomes uneconomic. Same at Colar, still going at depth. So we know these things can be very extensive once we find them at the surface, if they're steeply dipping like that. So we worked in Western Australia. Don't even try and remember the names because it's very difficult to remember names. But the important thing is we've got a whole lot of greenstone belts. Terrain's very similar, as I've said, to the Arabian-Nubian shield. Got ultramafic rocks, mafic rocks, andesites, tuffs, sedimentary rocks, conglomerates and so on, in a sea of granite. Lots and lots of granites in the terrain. So, in detail, what we did was we had Wiluna, we thought was the highest level deposit. The mineralisation, the metamorphism was sub-green schist fascies, so we put a student who's now one of the lecturers at UWA there. Mount Pleasant was the next one down. This guy, M.M.Ibrahim, works for Newmont. He works out of Ethiopia. Now, Norseman was a lot deeper. Guy Cam McQuaig is now director of the centre from which I retired, and Coolgardie, guy here, Joe Knight, is now heading up the BHP Billiton iron, manganese and so on division. And then we come down here with deeper and deeper down in here. So So we tried to put, this is just a schematic example of putting students on these different levels, trying to look at what the gold deposits look like at these different depths. Now the important thing is that we've got an ore fluid which is coming from somewhere. It's locally out of equilibrium with the rock. I've called this rock, this is just a basalt, let's say over here. The fluid has got more potassium and CO2 than the rock. So as it goes through the rock, it produces these alteration zones. So the first one might be just muscovite and dolomite or anchorite. Then it will go muscovite chloride and anchorite. Then it will go chloride and calcite and so on. So we'll see a series of very sharp reaction zones. And if we look at those minerals, we know something about the stability of the minerals. We can tell something about the temperature, for example. So muscovite isn't stable above about 500 degrees Celsius, so we know calcite isn't stable over 500 degrees. We see these sort of minerals there. We know that the ore fluid was like relatively low temperature. We see other minerals, we know it's high temperature. So if we look at one of these reaction zones, we can see this is a bedded rock. This is actually a banded iron formation through here with quartz and magnetite. So we've got magnetite bands and quartz bands. A little bit difficult to see the difference on the slide here. We can see it over here. We've got this reaction front, and it's moving through the units. The magnetite is more reactive, so the alteration tends to go along. And then the final product you can see here is a quartz carbonate rock with pyrite bands. The magnetite is Fe3O4, the pyrite's FeS2, the pyrite is replacing the magnetite, and the quartz just recrystallizes, and we get a little bit of carbonate, and we end up with a bedded rock. This is why people thought these were syngenetic. They look like syngenetic sedimentary rocks, but always you can find these fronts that show we're replacing the original rock along the front. If we look at high levels, say we would estimate we're looking at the top 300, top 3 kilometres of the crust when the gold deposits form. We find all sorts of brittle things. We find breccias. We can see here, these look like epithermal deposits, so-called epithermal deposits, but in epithermal deposits they formed more or less at the same time as volcanism. The volcanic rocks, these are all basalts originally. The volcanic rocks are about 2.7 billion years old, and the gold is forming 60 million years after the volcanism and after sedimentation. So it's got nothing to do with the volcanism, it's related to structure. You can see here, this is the normal ore. It's already brecciated. You can see the breccia fragments in there. Then you can see breccias inside breccias inside breccias. So this has been very low pressure, lots of brecciation, and finally filled with this carbonate matrix. Here we can see these were basalts. They've been very bleached. They're carbonate and sericite now. So they were once black rocks, and then they're surrounded by carbonate and filled with fine, cherty silica. And here we can see some beautifully banded rocks. So these are all low pressure rocks, lots of high fluid pressure breaking up the rocks, altering them, and then brecciating again. This was a dolerite once, this rock here, and we can see actually there's a boundary there. Right there, you can see this rock isn't veined over here, it's a bit altered but not veined. This rock is a more ultramafic part of the dolerite, it's a differentiated dolerite. So this is what we call a granifier.